Hello everyone. It's been a little while. I recently uploaded another video of me playing chess. It's fun, you know. I think I dunked on that guy real hard. Probably. No, I think I made some mistakes. And there was like 5 misses that game. Anyway, we're not talking about chess today. We're talking about something way cooler, right? So, for some of you, I made some videos programming. And as you can tell, I'm not a programmer at all. It's not my profession. It's not my trade. It's nothing of mine. It's just it's a hobby at this. Really, I wouldn't even call it that. It's more about just experimenting. Seeing what the craze behind programming is, and I can see it. I can see the appeal. Right, it's really cool stuff. What I'm actually, somewhat decent at is making electronics. That's my degree. That's what my 2 degrees are in. It's into making electronics, electronic engineering, and computer engineering. And so I thought I would show you guys some stuff with that. So we can just move on over to show you some stuff. So here on the screen, I'm using the Circuit.js, which is the Fallstad circuit simulator. You can find that online for free. To do so, you just open Google like so. You go to the Google search bar, and you search it fallstad.com/circuit. And the same thing, right? You can do full screen. There's a hyperlink in the bottom where I just clicked to download it if you wanted to just, use it offline and whatnot. And it has some cool features. You can see the flow of current. The conventional flow of current, that is, not the actual flow of current, but whatever, right? And then you have the scopes, so you can actually use oscilloscopes. Yeah, I mean, what else is there? You can also, well, there's no wire. Here's a wire. So you can go to the wires, and you can actually show the current and the voltage across wires and things. So that's cool and all. So yeah, I like this one. It comes with a bunch of preloaded circuits too. So let's say you wanted to take a look at an op-amp feedback, right? Usually, so what it looks like, maybe a feedback resistor here, or not, whatever. You have all different types of transistors, your combinational logic. So you can have a full adder. You can actually look at the ALU of a whatever this is, right? The Where are the numbers were, like the 74. Yeah, the 74181. Oh, there you go. There's your logic unit, which just so happens to also be full adders. I don't know. There's full subtracting capability as well. It might be whatever, right? But that's not what we're talking about. We're talking about cool stuff like logic gates. And so I made all these logic gates using diode-transistor logic. It's the logic family of like the 50s and 60s, if I'm not mistaken. And I did both. I'm showing you at the component level because like that's really the only way I can really show you what's actually happening, right? This abstracts away too much information. The logic blocks here, they abstract away too much information of what's actually happening in a circuit, right? So when you have a transistor, and then we have some resistors for keeping the current low, so we don't blow it up. And so the logic in diode transistor logic actually happens at these diodes here. So you'll notice we have a diode in reverse bias, then another diode that leads into the base of our transistor. We have these values actually aren't the right values, but it doesn't really matter for right now. But usually you use 4.7K, maybe 10K, and like the upper limit for diode transistor logic, right? Depending on what your input voltage or what your supply voltage is. So here we have a NOT gate, right? So all we do is invert the input. So now it's low on the output, right? So we have a high input, and so electrons can no longer flow through, or well, the current electrons, right? Whatever, same thing. They can't flow this way anymore, right? So they have to go through the base of the transistor, causing it to switch, and then now there's a path to ground this way. That's pretty cool. So to make a NAND gate in diode transistor logic, you can tell that all we did was add another diode for input, right? So look at that. 2 high inputs equals a low output. And you can test that with this NAND gate here, right? So same thing. Just to show you. And the AND gate. So how do we make an AND gate? Well, it's very easy. All we do is we just invert the output of our NAND gate, and we'll get an AND gate, right? So see, both inputs have to be high, otherwise it doesn't give us a high output. That's pretty crazy, isn't it? So then we have our NOR gate here, and our NOR gate, it's built using 2 NOT gates, right? And so usually you just prefer to use NAND if you can. Like if you're building an SR latch, you know, you can build an SR latch out of NOR. NOR gates tend to be slower than NAND gates, usually, so better off using NAND gates, right? Because you have less transistors. On top of that, you know, since we're talking about speed, I mean, if you're going for speed, you usually don't use diode transistor logic in the first place. You probably want to go for CMOS, or even transistor logic if you don't want to use CMOS. Oh, whoops, knocked her on the microphone. But yeah, here's our NOR gate, right? So does exactly what you would expect a NOR gate to do, right? One input makes it low. Why would we ever use a NOR gate? Oh, who knows, right? Who knows? And then your OR gate, obviously, is just doing the same thing with the AND gate. You just invert your output of your NOR gate, so either or both. And there's your 5 basic gates, right? Your primitive gate is your NAND gate. And you can see we're using less transistors in the transistor logic, right? For a NOT gate, we would have 2 transistors. I'm pretty sure for transistor logic, something, it looks a little bit like this, right? So we have our BJT, and I think this probably looks somewhat right. You know, someone will tell me if I'm wrong, maybe, if anyone ever watches these videos. Joke to myself. And then we just need one of these. Right, so this is your transistor logic inverter, or NOT gate. You can see invert, so you're using 2 transistors as opposed to diodes. Obviously, you know, I'm pretty sure it's faster as well, but it's kind of similar if you can see, right? You have the emitter here, then you're putting a current here. Obviously, the current can still flow through the emitter and into the base, as opposed to here, but you can kind of see how the evolution happened from diode transistor logic then to transistor logic, right? So that's cool, right? So using less transistors, so like for an AND gate, you would have I think three transistors. Then for a NOT gate, or for an AND gate, it would probably be like 5 transistors, right? So you're saving on transistors overall, and you can still get upwards of like 100 megahertz, maybe 50 to 100 megahertz in diode transistor logic, if I'm not making these numbers up out of nowhere. Obviously, this is a lesson to all of us that we live in the age of information, and instead of just making something up, we can just go, we can Google it. So let's go see real quick. How fast can diode transistor logic be? Oh, 1 megahertz. I'm completely off my rocker. Let's say we're using the 1N4148 diodes. Would the switching be any faster? Okay, this is the number I was thinking of. So, you know, supposedly, as the AI says, I don't know how true this is, right? But you can get up to 100 megahertz using the 1N4148 diodes, which is the fast switching diodes, or signal diodes. Yeah, you know, 4 nanoseconds, right? All the shit I was about to say, but now that the AI is saying it, if I say it, it looks like I'm reading the AI summary, so potentially 100 megahertz, right? I don't know how true that is. Maybe like 10 megahertz or 50 megahertz, right? I haven't built a circuit. Someone else can do research on that. Obviously, you're like, if you're using a 2N3904, I think that's like 300 megahertz maximum. If I'm also not making that number up, right? We're just not going to look it up because then I'm going to look silly. Like the first time I looked that up and then said, well, what if we're using the fast switching diodes, right? But there you go. Your basic gates, some basic information on that. And here we have our exclusive OR gate, which is the last real gate we really care about. I mean, you know, there's the exclusive NOR gate, but I mean, who the fuck's using that shit? So, you know, exclusive OR gate, it's either or, but not both. It's mutually exclusive. So high input here, we get a high output, but if we have a high input here and there, oh, we get a low output. But let's say we have a low input here and a high input there. Oh, it's crazy, right? And you can test that with this exclusive OR gate right here, right? Either or, not both. And then with our exclusive NOR gate, you can see our logic diagrams. And yeah, so exclusive NOR gates. It's the opposite of the exclusive OR gate. So, you know, oh, if we have one or the other, now it's low. But if it's both, then it's high, right? Oh, you could probably use that for some control logic or something, right? But that's your basic gates using diode transistor logic. I would show you transistor logic, but who cares, right? Who cares? Yeah, there you go. That's that transistor logic. It's pretty cool. So next time I'll show you guys some cool stuff you can do with these gates, right?